Welcome everyone to Rama, the 100x programming platform with functional programming at its core by Nathan Mars. We're glad that Nathan can join us today. Over to you, Nathan.
All right, thank you so much. So my name is Nathan Mars. Today I'll be talking about Rama. So what I love most about functional programming, and I've been a Clojure programmer for about 15 years, is how productive it feels. And I think the most important aspect of functional programming that leads to that productivity is composability. Lexical closures, functions as values, immutability, these let you express code as the composition of simple primitives rather than write what feels like small variants of the same code over and over. Now, there's a lot to talk about with Rama, but what I'll focus on today is how Rama brings composability to backend development, which has been severely lacking in backends until Rama. And that composability that Rama provides enables huge productivity gains. Now, when you say you've improved something by 100x, anyone who hears that will be skeptical, and you should be skeptical. So when we announced Rama a year and a half ago, we took it upon ourselves to demonstrate that 100x productivity improvement by building an application from scratch in its entirety. What we chose to do is rebuild Mastodon from scratch and make it scalable to Twitter scale. If you're not familiar with Mastodon, it's basically an open source Twitter. It's basically the same as the consumer Twitter product. There's a few minor differences. Mastodon has federation, Twitter does not, and there's other small differences around filtering and muting, but they're basically the same product. And we built the entire thing. And there's a lot of, it's just one application, but it's an application comprised of a lot of features that work very differently. The way timelines work is very different than how the social graph works, which is very different than how who to follow suggestions work, which is very different than trending topics and search and profiles and filtering and muting and so on. So what we did is we built it and then we actually ran it live. So anyone could join in and use it for about a week and a half. And we ran it with 100 million bots posting 3,500 times per second with 403 average fan out and a very unbalanced social graph where most people had around 100 followers and some people had over 20 million. And we then open sourced the whole thing. It's on our GitHub at this URL. You can download it, very easy to run locally, or you could run it yourself on a Rama cluster at scale. So if we compare the implementations of all these things, the Twitter consumer product, just the consumer product, took about 1 million lines of code and it's scalable. It's not that hard to build this product if it's not scalable. So pretty much all of that code was due to the expense of making it scalable. If you look at Mastodon, which is open source, the backend part of its implementation, not the front end, not including the front end, is about 16,000 lines of code, and it's not scalable. Like it cannot scale anywhere near Twitter scale. And then the Rama implementation of Mastodon is 10,000 lines of code, and it's scalable, just like the Twitter implementation. And along with that, the performance and scalability of our Rama-based implementation is as good or better than Twitter's implementation for the numbers that they have published. So here, for example, is a chart of the scalability of our Mastodon implementation. And you can see we tested it well above Twitter scale. Twitter scale is right in the middle there. And you can see, most importantly, that it scales linearly. The more resources you add, the more tweets per second that you can handle. This is a graph of handling the number of tweets that you can process per second and also deliver them to followers' timelines. By far the most performance-intensive part of this app. This is a chart of how long it takes for a tweet to reach your followers' timelines. So the P50 is about 500 milliseconds and the P99 is just under a second. Twitter's numbers was about 600 milliseconds for the P50 and something like 1.5 seconds for the P99. So we're significantly better on this number. And the last one I'll show, this is the time to render one page of your home timeline. So we were about 60 something milliseconds for that. And there's a lot that the backend has to do to render a page. You have to fetch about 10 tweets. You have to fetch all the content for those tweets. You have to fetch all the stats, number of retweets, replies, and likes. You have to fetch the information about the person who tweeted it. And if it's a retweet, you got to fetch more information about the tweet being retweeted. It's a lot of work. When I worked at Twitter, one of the first all hands I went to, the CEO got up and showed this chart for what their numbers were at the time. And it was something like 6-second average latency to render your homepage, which is completely insane. But it just goes to show that this is not something you get for free, and it requires engineering to get these kinds of numbers. So there's a few things that make building Twitter at scale challenging. So the first thing is that it has very diverse indexing needs, like the way the social graph, timeline, search, profiles, and many more features are stored and have to be computed is very, very different, and traditionally would require to use multiple databases. The second thing is the unbalanced social graph, which is really tricky to handle. So most people have 100 followers, but then some people have 100 million followers. So that means when someone with 100 million followers does a tweet, it's 1 million times more expensive to process that tweet because it needs to be delivered to 1 million times more timelines. And with a naive implementation, this will have a lot of problems. The first is fairness. If you're spending 1 million times more time processing that tweet from one of those big users, that can very easily delay everyone else's tweets from being delivered for minutes or more. And so that really ruins the product. The second is scalability. If you're a naive implementation, will process all of those followers on one node, which will massively skew the computation and essentially serialize it. So even if you're a distributed system, if all the work is happening on one node, you are not scalable anymore. So these things are very challenging to engineer. And the last thing is just there's a huge amount of writes per second because of fan out. If you're processing thousands of tweets per second and every tweet has to be delivered to 400 timelines, that is millions of writes that you have to do per second, which is a lot of load. There's a few reasons why Twitter's implementation ended up being 1 million lines of code, which may be surprising if you're not familiar with their implementation. The first is that Twitter had to build multiple specialized storage and computation systems from scratch. One of these, for example, was the timeline service. Timelines are kept in memory and unreplicated. And an interesting thing about your home timeline is it's redundant. It can be recomputed by looking at all the tweets that everyone you follow has tweeted recently. So you can always reconstruct it. And so the idea behind the home timeline, it's kept unreplicated, but if you were to lose a partition, you can reconstruct your home timeline on demand. So that's a very specialized, idiosyncratic storage service that Twitter had to build from scratch. Another one is their social graph. They needed a specialized database that they built from scratch to handle that and all the different ways they query that. Now, every time you have to build a database from scratch, that is a huge undertaking and very expensive. And you're largely doing the same kind of work that you've already done: managing processes, networking code, serialization, durability, replication, and so much more. It's very, very expensive. The second thing is just because of the number of tools they had to use to build it, including the ones they built themselves and the other ones they had to use, just a very high complexity for deploying, getting things to work together and configure them. And it really leads to a lot of cost. And ultimately, what this all comes down to is that they suffered from a severe lack of composability, where instead of being able to build the backend by composing simple primitives together, they're really just repeating themselves over and over every time they have to build one of these specialized systems. Now, another interesting comparison is Rama's implementation against the official Mastodon implementation, which, as I already mentioned, is not scalable. Now, the Rama version is 40% less code, even though the Rama version is in Java, while the official version is in Ruby, and Java is a much more verbose language than Ruby. The Mastodon official implementation, it's very typical stack. Postgres and Redis for storage, they use Ruby on Rails, and they use Sidekick for asynchronous processing. And this implementation suffers from all the usual stuff that backends have been suffering on for decades. It's complex to get these tools working together and integrate them, and lots of impedance mismatches. You have to make your application conform to these fixed ways in which these data stores allow you to store and represent data. Things like ORMs can help somewhat, but this has been discussed at length over the years. They only help somewhat, and they always leak eventually and cause complexity of their own. Okay, now you're not going to get the kinds of numbers that I've been talking about, 100x improvement in productivity, by just incrementally iterating on the ways people have been doing things for the past 50 years. It requires a fundamental shift in how you approach these problems. And that's what Rama is. It is a major paradigm shift in how you approach building backends. But it is built on some ideas that have been around for a very, very long time. They just haven't been explored to this extent. And those ideas are event sourcing and materialized views. Now, you can understand these ideas in contrast to how applications are mostly built today and have been built for a long time. The way you usually build applications, you have a separate application layer and a database layer. You do computation in your application layer, you do storage in your database layer. And your application layer does reads and writes to your database layer to drive your application. And your database layer represents the current state of the world. Now, your database layer may be comprised of 10 different databases, and an application layer may be comprised of an API server and queues and workgroups for asynchronous processing. This is still the model in which they fall under. Now, the idea behind event sourcing is to separate that. And the idea, and this is Rama's programming model, the idea is that rather than directly write to your indexes like you do in that traditional model, you instead write data into a log, just an append-only unindexed log. And in Rama, those are called depots. They are distributed append-only logs. And then what you do is you write ETLs, which means extract, transform, load. And that's code that consumes from your depot and then materializes as many indexes as you need to support your application. In Rama, those indexes are called p-states, which means partition states. And I'm going to have a lot more to say about this in a few slides, but Rama's p-states are much, much more flexible than databases. You shape every p-state to the exact shape you need for those use cases, and you make as many of them as you need. And the last part of the program model is querying. How do you actually query your indexes to actually support the questions that your application needs to answer? There's two kinds of queries in Rama. One is just called a point query. That's when you just query from one partition of one p-state. And the second is called a query topology, where this is a predefined, on-demand, distributed computation that can look at any or all of your p-states and any or all of the partitions of your p-states. And it's programmed with the exact same API as used to program ETLs. Another way that you can, I guess, visualize this program model, and this is the way I prefer to think of it, is like this. And for a functional programming conference, I think this is the preferred way for this audience. And that is to just think of it in terms of functions. And these right here are the first principles of backend development. Every backend that has ever existed fits under this, these two equations that you have here. And every possible backend that could ever exist fits under these equations. And what Rama is the most general possible expression of these principles, right? And the idea is every backend is some number of indexes, which is computed as a function of all the data you've ever seen. And then your queries are some function of all the indexes you've ever seen. And what Rama does is it lets you define your indexes as composable storage, lets you define your functions of your data that compute your indexes with composable distributed computation. It lets you store data however you want. There's absolutely no restrictions whatsoever. And then finally, computing your queries is also composable computation over your indexes. And to bring it back to the terminology I already brought up, data is depots, indexes are p-states, functions are ETL topologies, and functions of indexes are either a direct p-state query or a query topology. All this in Rama is programmed either with Rama's Clojure API or its Java API. There's no custom languages. There's no weird JSON or XML-based configuration or language. It's just a Clojure library or a Java library in its entirety. So to really help, I just want to show an example from the Mastodon implementation to help you understand this shift in thinking for how you approach building backends. And what you're seeing here is a diagram of the part of the Mastodon implementation that implements timelines, fan out, profiles, retweets, likes, scheduled posts, blocking, muting, and I think a few other things. And this looks intimidating, but it's actually only 1,100 lines of code, and it's implementing an absolutely huge amount of functionality. So the first thing I'll point out is the P states. So with each of those P states on the right, you can see which data structure it's using. And as you can see, it's using a wide variety of data structures, just showing that how useful it is to be able to tune your indexes to precisely the shape that perfectly matches those use cases. But what I want to point out is that fan out ETL right there on the left in the middle. And that's the part that handles delivering tweets to your followers' timelines. Now, traditionally, this happens in an application layer that's outside your database. And there's a lot of just business logic that goes in there. If it's a retweet, don't send that tweet to the person who originally did that tweet if they happen to follow you. If it's a reply, only send it to people who also follow the person you're replying to. Otherwise, you send it to all your followers. So whereas traditionally this exists in the application layer, in Rama, it exists inside Rama, right? It's kind of like it existing inside your database, but Rama is doing a lot more than a database does because it's also doing computation. It's co-locating computation and storage. Okay, a few more things before we dive into the abstractions, just so you understand what Rama is. Rama is deployed as a cluster, and you deploy any number of Rama applications, which are called modules, onto that cluster. And part of deploying a Rama application is specifying how much parallelism you want. So maybe one module is running on 4 nodes, another module is running on 150 nodes, and maybe another module runs on only 1 node. There's 2 kind of nodes in the cluster. The conductor, there's just one conductor node. That's a central node. No data processing goes through it. That's just used to do module operations, deploy modules, update modules, scale modules, and et cetera. And the conductor coordinates that across the cluster. Second kind of node is called a supervisor node. Supervisors listen to the conductor to understand what they should be running. And so when they find out they should be running a module, they'll download the code and they'll launch workers to run your module. Deploying and managing modules, it's all done with the Rama CLI, and they're all one-line commands. So launching a module looks like this. You just say deploy, you give it the jar containing your code, you tell it the name of your module, and then you say how much parallelism replication you want. Updating a module is similar, but shorter. You just say update, which module you want to update, and what a jar containing the new code. And then scaling is similar. You just say which module you're scaling, and you give it the new parallelism settings, whether you're scaling up or down. And then Rama handles all the coordination of doing these commands in a fault-tolerant way. Last thing, in terms of just operating Rama, a really cool thing about Rama, since it's such a general platform, is that we actually use Rama to implement a special module that monitors all the modules, including itself. So that's called the monitoring module. And so it collects, processes, indexes, and visualizes very detailed telemetry data on all aspects of modules. And just to show a very small sample of it, like here's some telemetry on the running of ETL topology, a microbatch topology. This would be aggregated GC telemetry for all workers for a module. And this is query telemetry for a P state. And there is a ton of telemetry here. I'm not even scratching the surface here. Okay, so let's get into the fun stuff, which is Rama's abstractions, which are very different than anything that you've used before. So Rama's P states, which, as I said before, means partition state. You can understand it in contrast to databases. So every database has what they call a data model, a fixed data model, key value, column-oriented, document, graph, relational, etc. And that data model dictates, or that is just what the database does. That is how it indexes data, and it determines the entire API of what kind of operations the database can do, how it can fetch data, and so on. Now, Rama, P states are defined not as data models, but as data structures, maps, sets, and lists, and so on. and they're as composable data structures. So every p-state you create can be whatever combination of data structures you want. And it turns out every data model is just some particular combination of data structures. Key value is just a map. Column-oriented is a map of sorted maps where those inner maps can be very, very large, can be larger than memory. A document database is just a map of maps, and so on. So data structures can very easily mimic any data model, but then because they're composable, they can do literally infinite more, any data model you could possibly imagine. And it's all based on the composition of the simple primitive of data structures. And every p-state you create is durable, distributed, and incrementally replicated, which are all the properties you need to be able to replace what you currently use databases for. So here's some examples using Rama's Clojure API of defining some p-states. So on the top left, this would be a p-state that's like a key value database. It's a map, in this case, a map of strings to longs, right? On the top right, this is a value p-state. So this is saying that every partition of the p-state is a single long value. Might take a second to wrap your head around it, since you're probably used to every database is based on the concept of a key, which is ultimately based on the concept of a map. But you're not restricted with that in Rama. You can have every partition just be a value. That value p-state, one example where you might use that is for ID generation within a topology. On the bottom left is the same as a column-oriented database. It's a map of maps where that inner map has, you can see it has that property subindex true. And what subindexing means is that rather than store that inner map as a single value, it stores the keys and values individually, which basically means that that inner map can have 10 billion entries in it, and you can still read and write to it efficiently. And on the bottom right is an example of how you might go about doing a graph type data model. So here we have, this is like the type of graph you might have in a social network. So here, like the keys would be, let's say, a user ID, which would be, let's say, a long. And then the value of that is a fixed key schema, which all that is, it's a map with a predetermined set of keys that are allowed. And each of those keys can have a separate schema. So it has a key called props, which are just some properties on that user, name, birthday, location. And then friends is a subindex set of other user IDs, right? So with this example, you can really see how you're able to compose data structures together to tune your indexes to precisely what is most optimal for your application. And here is how p-states would exist in a full module. We haven't talked about a lot of this stuff yet, but I'll just briefly go over it. So here we're defining a module called bank transfer module. This comes from, we have an open source repository called Rama Demo Gallery, and this is one of the examples in that repository. And what this module is doing is showing how to do atomic exactly once transfers of funds between two bank accounts. So it's basically doing a cross-partition transaction. But here we have two depots. One represents transfers, another represents deposits, creates a microbatch topology that's going to do the processing, and then it declares some p-states for that topology. These are the p-states that topology will materialize. So we have funds, which will store the number of funds for every user, and then we have outgoing transfers and incoming transfers to just keep track of all the transfers that have happened for that user and whether that transfer was successful or not successful, right? And then it's cut off at the bottom, but at the bottom is where it starts defining the code that actually specifies how to materialize those p-states from those depots. Okay, so with such a generic expressive way to express your storage, you need a correspondingly expressive way to query and manipulate that storage. And Rama provides that with a really cool abstraction called paths. And I'm going to explain paths through example. And I'll be doing it with this example p-state, which is a map of lists. And just imagine that p-state has that data on the left, right? A map of lists. So here is a simple query to grab one piece of information nested within that p-state. So up above, you can just see what it looks like to grab a client to a p-state from, let's say, your API server or your REPL or wherever you need to interact with your module from. And then that query is that foreign select one call. And that first argument to that call is a path. And what a path is a sequence of what are called navigators, which specify how to hop through your data structure to get to the data you're interested in. And you can see it visualized below how those navigators work. So A0 will navigate to the value for A0, which is that submap. A1 navigates to the value from there, which is that sublist. And then nth path 1 navigates to index 1 of that list. And so this whole query ends up returning 3. Here's a query that selects multiple values from the P state. So navigators can navigate to multiple values. So here the path A0, same thing, goes to that submap. And then map vals goes to every value of that submap. So we're navigating to both of those, and the subsequent navigation will be on each of those. So all will navigate to every element of that list. And so we end up selecting all those subvalues 93608. This is the same thing, except it's also adding a filter at the end to only keep values that are less than 7. So that pred less than 7 just filters at the end. So we only end up getting 3, 6, and 0 as a result. Okay, so that's really cool. That's how you do queries. That is just scratching the surface of the query navigators, but that's the general feel of what it looks like to interact with P-states for querying. So let's look at transforms. So same idea, transforms are about navigating with the addition of you have to say what you want to do to the values that you navigate to. How do you want to change them? So I'm going to show you 2 simple examples, and then I'm going to show you 1 mind-blowing example. So this example navigates to A0, to A1, to the second element of that list. And then that term function says what we want to do to the element of that list, which is here we say we want to increment it, right? So you can see how the P-state changes, that value 6 turns into a 7. This is all this transform path does. Here's another transform that is going to change multiple values. So we go to A0, we go to every value that match, which are all those lists. We go to every value of those lists. We only stay at the even numbers, and we are going to decrement all those even numbers. And you can see 3 values now got transformed with that transformation. Okay, now let's look at a really crazy one. So what this transform is going to do, it's going to navigate to all the even numbers for all keys, for all lists that are nested within this map, and it's going to reverse their order while keeping everything else the same. So you can see if you look on the bottom, the 2 got swapped with the 12, the 10 got swapped with the 10. Sorry, the 10 got swapped with the 4, and the 8 got swapped with the 6. And the way this path works, you can see to navigate to all the even numbers, it's map vals, all even, basically the same thing we've been seeing, but that's wrapped in a subselect. And what subselects means is that we're going to take that subpath and we're going to navigate to all of those values, but as a list. So the subsequent navigation will be on that list, but subselect, it's kind of a virtual list. It remembers where those numbers came from. So then when we do term reverse, which reverses the order of that list, it reverses them where they originally were, which is pretty cool. Now, I've never had to do a transformation like this in a Rama application, but that's not really the point. What you're seeing here is a pretty crazy transformation expressed very concisely, just showing the power of a composable abstraction. The actual interface to this composable abstraction couldn't be simpler. All navigators implement this interface. So there's one code path for querying, which is select star, another code path for transforming. And this particular implementation is for how you navigate to the value of an associative data structure by a key, right? Which is, we saw many examples of that already. So it's very, very simple. And it's incredible that just so much power emerges from such a simple interface through the power of composition. Okay, let's now look at composable computation, which is the other side of Rama besides storage. And the key for what you need to be able to have computation API that's able to handle any use case at any scale is you need distributed programming to be as natural and expressive as local programming. Variables, conditionals, loops, anonymous operations, and the ability to decompose your code, just like you would in any program that you do when you're just doing a single process program. Now, in addition to that, you need to be able to seamlessly intermix what you're computing with where you're computing it. And this is the really big breakthrough of Rama's computation API, which is allowing you to intermix what and where kind of at will. Now, just like how Rama itself is based on ideas that have been around for a very long time, event sourcing and materialized views. Its computation API is also based on an idea that has been around for a very long time, which is continuation passing style. Now, continuation passing style, maybe you encountered it in college and haven't encountered it since. It's not something you should do manually because it's really verbose and it's unreadable and it's ugly. But what Rama does is it enables continuation passing style to be done elegantly and powerfully. So here's an example of continuation passing style in Clojure. Basically, all it means is that the last argument to the function is going to be the continuation. So it just means instead of returning a result to our caller, we're going to pass our result to our continuation. So the identity function in CPS would just be, we call a continuation with the value we were passed. And so if we want to compose print line with that, print line is the continuation. We say identity CPS, hello world print line, and that prints hello world. Here's an example of doing some arithmetic with CPS. So here is plus, times, and minus, defining continuation passing style. And then we're going to add 1 and 2, multiply that by 3, and then subtract 1 by composing them like that. And as I said, doing continuation passing style manually, it's gross, it's verbose, it's unreadable, lots of nested functions, and don't do this at home. Okay, so let's look at how Rama exposes continuation passing style. So here is Rama's version of the identity function in continuation passing style. So Rama, just like how you have defin in Clojure, and Rama you have def Rama op. And the continuation to the def Rama op is implicit. So here we're defining an op called identity Rama. It takes in one variable called v. All variables in Rama are symbols beginning with a star. And then what this is doing is it is emitting v to its continuation. So that little colon angle bracket keyword that looks like an arrow just says emit to my continuation. It's the same thing as in the Clojure version where you call your continuation with the value v. And then bottom right, you can see how you can call that little question mark arrow operator. That's not something you use in modules. This is just for playing at the REPL, just lets you run some Rama code in the context of a Clojure REPL. So here we say identity Rama hello world, and then that colon angle bracket arrow keyword again. When invoking an operation, it separates your input from your output. So here we're saying our input is hello world, and our output is going to be a variable called s, which is going to be bound to anything that operation emits. So we're going to take that variable, and then we're going to print it, right? Identity Rama hello world emits to the variable s, and then we print s, and this is going to print hello world, just like the Clojure version. You can also nest expressions in Rama, and this Rama compiles it exactly like the previous version, right? So it looks exactly like Clojure code, but it's actually compiling as CPS as data flow. Here's what that arithmetic example looks like in Rama. So all the nested functions are gone, and it composes much more smoothly. We add the numbers to bind v1, we multiply v1 by 3 to bind v2, and then we print v2 with 1 subtracted from it. Okay, now you might be wondering why I'm going on about continuation passing style. And the reason is because when your continuation is explicit, you don't have to call it just one time. You can call it many times, you can call it 0 times, you can call it a dynamic number of times, and most importantly, you can call it asynchronously. And that is what is going to unlock distributed programming for us. So like here's an example of calling continuation multiple times, right? So you can see on the left, emit many times CLJ, it's just going to call the continuation 4 times with 1, 3, 2, and 5, right? Same thing in the Rama code, except we just emit 4 times, 1, 3, 2, and 5. Both of these do the same thing and print those values 4 times, right? Again, the Rama code, you can nest the expressions, and this looks like Clojure, but it's definitely not running like Clojure because that print line is executing 4 times because emit many times emits 4 times, right? Because that factors like this. So it's running a print line for every single time emit many times emits. Okay, here's an example of how an operation can emit 0 times. This is the filter operation, which comes just as part of Rama's core library. And this just says, if the value provided to it is truthy, then emit. Otherwise, don't emit, right? Looks almost exactly like the Clojure version. And like here would be an example of using it along with our emit many times operation, right? We emit many times to bind v, we filter on if the value v is odd, and then we only print if that filter emits, which will only be for odd values, right? So this emits not 1, 2, 3, 5, but just 1, 3, 5. And the interesting thing about this is that this actually looks a lot like the kind of code you write on SQL, and that we have this expression on this one variable, and it's almost like we're doing, like set algebra, like you do with SQL. And that's another thing Rama does, which we don't have enough time for in this talk, but all the types of things you can do with relational programming, like aggregation and subqueries, outer joins, inner joins, all that stuff, Rama can also do those things. Interesting thing about data flow is it also unifies with relational programming. Okay, here's an example of an operation emitting a dynamic number of times. So Rama has an operation called explode, which will emit for every value in the sequence, which could, of course, be of any size, right? So this would be one way to print every value of a sequence. Another thing you can do is anonymous operations, just like you can in Clojure. So here we're defining an operation called adder, which takes in a value v1, and we're defining an anonymous operation, ret, which takes in as input a value v2, and it emits v1 and v2 added together, right? The Clojure code for this is a little bit hard to read because of all the continuations. But you can see the way we use it, we call adder on 10 to get this anonymous operation. We invoke the anonymous operation with 3 to get the result val. We print that and we get the result, and that's just 10 and 3 added together, right? Anonymous operations are very similar to Clojure anonymous functions. They capture the lexical closures, and they kind of just work exactly how a Clojure anonymous function would work. Okay, so now let's get to the really cool part, which is emitting asynchronously. And let me just explain a little bit about how Rama modules work so that you can understand the code I'm about to show. So a module, when you deploy it, it looks like this. With a module, you specify how many tasks your module should have. And every task is a partition of the module, and every task has a partition of every p-state and depot on the module. Every task also has an event queue and an executor thread that is running events off that queue, and those events have access to all the p-states and depots that are on that task. And when you're programming a Rama module, your code is always running on one particular task, but then you can jump around tasks very easily with what I'm about to show you. So these operations that emit asynchronously, the ones that Rama provides, are called partitioners. Partitioners are otherwise exactly the same as other operations in that you give them input and then they can emit any number of times. The only difference is that they emit asynchronously. And what a partitioner does is it computes which tasks to emit on, and then it transfers its continuation to those target threads and nodes. So one of the most common ones to use is called the hash partitioner. It just takes in one argument, and it computes the target task by taking that argument, hashing it, and then modding that hash by the number of tasks. This has the effect is that the same argument always goes to the same task, but different arguments are evenly distributed across all tasks just because of the properties of hash functions, right? So on the bottom, you see just some pseudocode, basically from the bank transfer example, which I mentioned, where we hash by from user ID to get to the partition where we're storing the funds for that user. We fetch their funds from the p-state. We only continue the transfer if the number of funds they have is at least the amount of the transfer. Then we deduct that amount of money from that user. Then we hash to the partition storing the funds for the user we're transferring to, and then we add to the funds for that user on that p-state. So this is very, very typical kinds of programming to do with Rama. This is what the implementation of partitioners look like. I think I'm running short on time, so I'm going to skip this part. Yeah, you can find out more about this by looking at our blog where we wrote about this topic. Over here is just an example of how partitioners can, they don't have to go to just one task, they can go to all your tasks, or they can go, the global partitioner always goes to task 0. I'm just going to skip that stuff since we're running out of time. Okay, now the key thing here about Rama's data flow language, as I mentioned, is that partitioners are no different than any other operation. And that uniformity enables composition. This means you can use partitioners just like any other language construct, like conditionals and loops. So if you want to do a looping computation, which is jumping around different nodes, grabbing different things, all accumulating into one list, that's very easy to do. And it looks very similar to how you would do a loop in Clojure code, except you're jumping around the cluster with impunity, right? This code sample at the bottom is an example of looking at a P state, which contains parents, so like kind of like a graph P state, and then fetching all the ancestors starting from some node ID. So this is intermixing loops with partitioners and conditionals very, very easily. The last piece to this, in terms of how your P states are connected to your depots through data flow, is with this sources macro, which when you're defining a module, it enters data flow mode. These source expressions specify subscriptions to your depots. So it creates a reactive computation. Whenever that depot has a value appended to it, it will then emit to that subscription, and that's how your data flow computation starts, where you can then read and write from P states, jump around the cluster with partitioners, and do whatever your computation needs to do. Okay, so to summarize Rama's data flow language, it's very similar to Clojure, but also with the ability to control where you execute just as easily as what you execute. And all the details of making that happen for routing, serialization, and closures is all handled automatically from you. And it makes it absolutely trivial to jump around the cluster to query and transform any partition of any P state that you need to interact with. And to summarize Rama as a whole, for everything I just showed you, Rama provides composable storage and computation abstractions for building applications in any domain at any scale. So what previously required building specialized tooling can instead be built quickly by composing these much simpler primitives together, as we demonstrated with our Mastodon application, right? The computation and storage techniques we use are very similar to what Twitter did, but we were able to build them as the composition of simple primitives rather than need to build these specialized services from scratch. And the last thing is that the other big benefit of composability is that it eliminates impedance mismatches by allowing you to mold Rama to your application rather than need to twist your application to fit the arbitrary data model and restrictions of a database. There's a ton I didn't have time to cover, but all very important topics. So I just want to just mention them briefly. The first is that Rama has ACID semantics that are as strong as Postgres, but they're actually simpler to use because you never have to specify isolation levels, which are a very complex thing to reason about. And the reason you never need to specify isolation levels is because Rama co-locates computation and storage, so you always just get the ideal semantics automatically. Everything in Rama is fault tolerant, both computation and storage. So there's always topology fails, it will retry according to how you configure it. Stream processing is either at least once or at most once processing, depending on how you configure it, while microbatch processing is exactly once processing. It's a cross-partition transaction in every case. I mentioned this briefly, all storage, all state in Rama is replicated. It's incrementally replicated as opposed to snapshot-based replication. Snapshot-based replication is a lot easier to build, but if your leader dies, it could take minutes or longer before the follower is ready to be able to take over. With incremental replication, a follower is always ready to take over immediately. One of the really cool features of Rama is fine-grained reactivity, which is actually a new capability. It uses the exact same path API I showed, and enables you to do reactive queries, where you query for a particular value of a P state, and Rama tells you not just that the value changed, but exactly what changed about it. Another really cool thing in Rama are these instant P state migrations. Evolving an application is very important. Your P states are going to change. Rama lets you change the schemas of your P states and have them apply instantly. Even if your P state is 10 terabytes, your migration goes through instantly. Wrote about it on our blog. It's really cool how that works. And last thing is incremental backups. We're just about to release this, but you can back up all Rama storage incrementally to an external store like S3. Okay. So lastly, we're currently in private beta, but we are very close to finishing the private beta, entering general availability, which will include releasing a free version of Rama. The free version will be limited to 2 nodes, but that's actually good enough. Like for any kind of application you currently build with, let's say, Postgres and API server, you could do that with Rama instead with that scale. Paid licenses will be for larger clusters or for anyone who needs enterprise features. If you'd like early access to the free version, you can email us at beta@redplantlabs.com, and I'd be happy to give you early access. If you just want to try out Rama right now, you can do so by downloading our public build, which lets you run Rama clusters simulated in process, which is actually the test environment for developing Rama modules. You can see how to get that from that link. And as I mentioned, Rama Demo Gallery is a project already pre-configured using that and has lots of examples that you can run and play with. If you'd like to keep track of what's going on with Rama, you can sign up for our mailing list at the footer of our website. You can join the Rama channel on Clojarians, or you could follow me on Twitter or Blue Sky at Nathan Mars. I think I'm out of time, so I won't be able to answer any questions, but I will be on the Hangout room after this. So thank you so much for listening.
Thanks, Nathan. Thank you so much.